if you have like a molecule, I'm going to call it X, that has nothing but single bonds on it, all single bonds come from hybridized orbitals that make sigma bonds, and you have to have 4 hybridized orbitals, you must have an sp3. Okay? So the sigma bonds and the lone pairs are always hybridized orbitals. Sigma bonds and lone pairs are always hybridized orbitals. So if I have X with a lone pair on it and 3 single bonds, that's also sp3. Or if I have some element with 2 lone pairs and 2 single bonds, that's still sp3. Or if I have something that has 3 lone pairs and 1 bond, that's sp3. Okay? Now if what I have is an element that has a double bond, okay, and maybe 2 single bonds, well, that double bond has to have 1 unhybridized orbital, but it's got to have the sigma bond here has got to come from hybridized orbitals, and both these sigma bonds here have to come from hybridized orbitals. That's 3 hybridized orbitals. That means this must be sp2. You can also have a double bond and a lone pair and a single bond. Okay, you can also, that's sp2. And you can have a double bond with 2 lone pairs, and that's sp2. Okay? So then if you have something that has a triple bond and a single bond, then I've got to have 2 sigma bonds, which come from hybridized orbitals, and 2 p orbitals that are not hybridized, so that must be sp. You can also have a lone pair and triple bond, or you can have 2 double bonds. All of these are sps. Okay? So what you need to do is you count the number of sigma bonds and lone pairs. That tells you the number. That tells you how many hybridized orbitals you have, and figure out which hybridization gives you that many. Okay? Yeah. I'd much rather you understand how it works than try to memorize those things. But, yep. Nobody knows when it splits. It just does. It's like half-lives with nuclear. Nobody knows when any individual particle is going to split. We just know they do periodically. Yep. It just does sometimes. Not initially. It only joins up with the nitrogen on an ammonia if you put ammonia in water. Autoionization is something that's going to happen in water whether or not there's ammonia there. Okay. I think it would be helpful for me if you would get these people who are talking out to be quiet so I can hear you. Oh. All right. No, if you have, for a double bond, you have to have a p orbital going this way, making a pi bond, and you have to have a separate p orbital going this way to make a pi bond. So if I've got 2 p orbitals, then I also have to have a sigma bond that comes from a hybridized orbital. The only thing that works that out is an sp. sp has 2 hybridized orbitals and 2 unhybridized p orbitals. If you do the 3-dimensional thing, where you're showing sigma bonds, you got 2 in a pi bond. You got sigma bonds, and you've got a pi bond. Okay, so that's 2 bonds going this way. Well, to make a second bond going this way, I've got to have another pi bond. If that makes any sense to you when I do it that way. Okay. All right. What's next? What's the next question? Autoionization of water. You know this is on like page 2 of the handout, right? Okay. So what's happening in autoionization is one of these hydrogens, doesn't matter which one of these is going to leave, and it's going to leave behind the electrons. The electrons are going to stay on the oxygen. So when the hydrogen leaves, what actually happens is it's a hydrogen ion, proton. So the result is that over here on the other side of the arrow, we actually have that hydrogen ion, and what's left then are all the electrons. So there's one more electron than protons over here, so this has a negative charge. Then this hydrogen then can go along and either rejoin this and form water. It can join up with the water to make hydronium. Or if you put ammonia in the water, it can join up with an ammonia to make an ammonium. Covalent compounds generally are softer. Ionic compounds are generally harder, except for covalent network crystals. They're harder than ionic compounds. So diamond's example is an example of a covalent network crystal.